Welcome to my talk about near-optimal scheduling in the congested Clique. My name is Volodymyr Polosukhin, and this work is done together with Yannick Maus and Professor Karen Sensor-Hillel. There is a growing number of platforms for parallel and distributed computing, like Hadoop and Spark. Computer farms have large queues of jobs. Our goal is to develop a framework that executes distributed jobs as fast as possible. The theoretical model, designed to simulate distributed systems with all-to-all communication, is a congested Clique model introduced by seminal work of Volodymyr et al. In 2003. In this model, there are n machines, with identifiers from 0 to n exclusive. In each round, each pair of machines can exchange one message. Usually, local computation time and memory usage are not bounded. Message size in this model is order of log n bits, just enough to encode identifier. The complexity measure in this model is the number of rounds till the last node terminates. Consider maximal independent set problem, where the system is required to compute the set of nodes which are not connected with edges and which we cannot extend without breaking this property. In the distributed settings, each node originally knows adjacent edges, and each node should output a single bit. The node which outputs enabled bits should form MIS. Ghafari et al. Showed how to compute MIS in order of log-log delta rounds with high probability in the congested Clique model. We still do not know if we can go down to order of 1 rounds. However, scheduling routines we show in this paper, used as a black box, allow us to run multiple instances of a MIS problem in constant number of rounds amortized. In addition to being an interesting question on its own, in the past it has been shown that solving multiple instances of the same problem is beneficial for solving complex problems. Consider a minimum spanning tree problem, where nodes required to compute which of their edges belong to minimum weight tree spanning the entire graph. Hagemann et al. Reduced this problem to multiple instances of sparse graph connectivity problem, where nodes require to check if some graph is connected or not. This allows the authors to break below the long-standing order of log n upper bound by Volodymyr et al. Most MST algorithms use similar reduction. Ghafari and Novitsky show how to run polynomially many instances of MST problem in constant number of rounds, and use it to solve a minimum cut problem. In this problem, each node should join one of two sets such that the number of edges between the sets is minimum. State-of-the-art minimum cut algorithm by Ghafari, Novitsky, and Sorup runs multiple instances of graph connectivity problem. In the all pairs shortest path problem, each node is required to learn the distances to each other node. State-of-the-art exact APSP algorithm by Legal reduces distance product to multiple instances of matrix multiplication. In the scheduling problem, we are focused not only on the set of instances of the same problem, but also in running set of different problems with different inputs. Those problems can be graph-related, like minimum spanning tree, maximal independent set, or algebraic, like matrix multiplication or determinant computation. The distributed system is required to produce the output to all of these jobs. Originally, the input for each job is provided in distributed fashion. For graph-related problems, each machine knows the adjacent edges of the corresponding node. For algebraic problems, each machine knows corresponding row and column of input matrices. Each machine knows the protocol of each job. After some communication rounds, each machine is required to produce outputs of the corresponding nodes from each job. For example, if one of the jobs was computing maximal independent set of the graph, each machine should hold a bit if it belongs to MIS or no. Before talking about the results, let us define the properties of the jobs we are going to use to describe the complexity. First one is dilation. It is the round complexity of the slowest job. Notice that the dilation is clearly a lower bound for round complexity of the scheduling. Another property, this time related to message complexity, is edge congestion. To compute it, for each edge one sums over all rounds and over all jobs the number of messages sent over that edge. Then one takes the maximum over all edges. So, the congestion of the set of jobs is the maximum number of messages that need to be routed over a single edge of the network. This is a good metric for related congest model, which is similar to congested clique, but allows communication only over the edges of the input graph. In the congested clique model, the edge congestion is not a suitable metric, since up to n messages can be delivered between a pair of nodes in a constant number of rounds using intermediate nodes. This inspires us to define local congestion. To compute it, for each node we sum over all rounds and over all jobs the number of messages this node sends or receives. Then we take maximum over all nodes and normalize it by sending or receiving capacity n. So, local congestion is the maximum total number of messages all nodes assigned to one machine has to send and receive over all rounds, normalized by send receiving capacity n. This is a natural lower bound of scheduling jobs under certain assumptions of the scheduling algorithm. Finally, we define global congestion as the total number of messages all nodes in all jobs and over all rounds. Basically, the sum of message complexities of all jobs, normalized by n squared per round bandwidth of the congested clique model. This is clearly a lower bound for the number of rounds scheduling of the set of jobs takes. Notice that the local congestion can be significantly larger than global congestion. Consider a protocol where each node sends a message to a leader node with identifier 0. Assume it does so for order of n rounds, like in the case where a leader learns the entire graph. Assume that there are order of n jobs like that. Node with identifier 0 receive order of n cube messages, and those are all messages in the system. This means that the local congestion is order of n squared, while global congestion is only order of n. Now let us go over results. Firstly, we show an algorithm to schedule square root n jobs which require square root n log n bits of memory in order of global congestion plus dilation rounds. This is optimal up to a constant factor, as both global congestion and dilation lower bound the scheduling time. Secondly, we show an algorithm to schedule I/O efficient jobs, which are almost all graph-related jobs in the congested clique model. We schedule t such jobs in order of t plus global congestion plus dilation times log n rounds with high probability. Finally, we apply the random delays method Leighton, Marks and Rao developed to obtain another scheduling algorithm in order of t plus local congestion plus dilation times log n rounds with high probability. Most of our algorithms does not require the knowledge of the job's communication pattern or their other non-trivial properties and adapt to the protocols on the fly. Several years ago, Ghaffari studied a scheduling problem in the similar congest model. Unlike congested clique, in the congest model, nodes can send and receive messages only to their neighbors in the input graph. This means that the communication graph is not necessarily a clique anymore. The authors used the random delay technique developed by Leighton, Marks and Rao to schedule with high probability distributed jobs in order of congestion plus dilation times log n rounds after order of dilation times log square rounds of preprocessing. Here also shows the complement in lower bound. Now I will present you with the main scheduling results and give some intuition about how we obtain them. Let us start from our first scheduling, which is deterministic. In this algorithm, we schedule memory-efficient jobs in close to optimal order of global congestion plus dilation rounds. All our algorithms have a similar high-level structure. They work in epochs of phases, where on each epoch, all jobs will move from one round to the next round. Machine simulates nodes and send messages on behalf of those nodes. Job index and node sender receiver identifier are a part of the message. Back to our deterministic algorithm. For the epoch where MR messages are sent overall, we would like it to run in MR divided by n square rounds, exploiting the entire bandwidth of the congested clique model. Take a look at the picture. Messages of different jobs are represented with arrows of different colors. Despite the fact that overall jobs want to send at most order of n squared messages, it might happen that the set of locations nodes assigned to the same machine want to send significantly more than messages, so it cannot send it in constant number of rounds. We overcome this problem by reassigning nodes between machines. This is the idea behind our deterministic algorithm. The communication bottleneck might be in different places for different rounds, and since we do not assume the knowledge of the communication pattern beforehand, we have to reassign nodes between machines on each round. Notice that our algorithm also does not assume the knowledge of global congestion or dilation. To do the reassignment efficiently, we require some assumption on the jobs being scheduled. We assume that the state of the node can be represented in n log n bits. This assumption allows us to reassign nodes efficiently. There is additional little subtlety here which I am not mentioning here to simplify the presentation. Let me describe the algorithm for a single epoch. We want to execute an epoch where all jobs together send MR messages in complexity as close as possible to MR divided by n square rounds. Let us first start with a simpler case, where we have n squared messages, and try to execute them in as close as possible to constant number of rounds. Take a machine which currently simulates t, say, square root n nodes, represented by different colors. For each node, it knows how many messages it is going to send and receive. Those numbers are bounded by n. We locally greedily split those nodes into buckets that send and receive order of n messages. Then each machine broadcasts the number of buckets. We show that overall the number of buckets is order of n. So all machines compute the same greedy assignments of buckets to machines, such that each machine gets constant number of buckets to simulate. After we computed the assignment, we reassign the states according to it. Each machine originally had t nodes to simulate. Thus, bucket also has at most t nodes. The assignment assigns a constant number of buckets to each machine. Thus, each machine has to send and receive at most order of t job states, where each state can be encoded in m log n bits. Consider the old setting where m is square root n and t is square root n. Using well-known routing scheme for the congested clique model, we can do the reassignment in constant number of rounds. Recall that the assignment we computed is designed in a way that each machine sends and receives order of n messages. Also, the assignment is globally known. Take some message. The machines which simulate the sender after reassignment knows which machine simulates the receiver after reassignment. So we can simulate the sending in constant number of rounds using well-known length and routing scheme. After executing the local computation of the next round, we send the states back to the original machines. There also might be a case where all jobs together want to send more than n square messages in the epoch. Denote this number of messages by MR. In this case, we shall do what mathematicians know to do best. We reduce the general case to the previous case. We use n research to split jobs into chunks, where each chunk sends order of n squared messages. Then we execute this chunk one after another using the previous approach. This allows us to obtain the required round complexity. Let us move to our second result, which is randomized scheduling in order of t plus global congestion plus dilation times log n rounds with high probability. We want to remove the assumption of jobs be memory efficient. However, we still want scheduling close to global congestion and dilation lower bound. And here randomization comes in handy. We show that if we randomly shuffle the input of each jobs denoted by icons of different colors before the execution, the following execution will take only global congestion plus dilation times log n rounds with high probability. In this algorithm, we also do not assume the knowledge of global congestion or dilation of the job set. To do the shuffling and unshuffling efficiently, we assume that input and output for each node is order of n log n bits long. Notice that this assumption holds for almost all studied algebraic problems, where each node is given row and column or square matrix. It also holds for many of the graph-related problems, where a node is given at most n adjacent edges and produces n log n bits of output. For example, in the maximal invariant set problem, each node outputs a single bit indicating where this node belongs to a set or no. In the minimum spanner tree, each node outputs a subset of its adjacent edges that belong to the tree. Let me briefly describe the algorithm. First, the leader node, sequentially, for each job, generates a permutation. It informs each node, represented by a different color, about its order in the permutation, and the nodes broadcast their indices. Finally, they use non-routing scheme to actually permute the inputs. For each job, this process takes a constant number of rounds. Thus, overall, it requires order of t rounds. Then we execute jobs in phases, where on each phase, all jobs progress to the next round. We use halving and union bounds together with a well-known routing scheme to show that we can deliver all MR messages of round R in round complexity that is optimal up to additive order of log n rounds with high probability. Finally, after all protocols are finished, we unshuffle jobs output using the same approach as we did when shuffling inputs, and we obtain the claimed complexity. And now briefly about our last scheduling result. We use the random delays method of Layton's Max and Rao, motivated by its application in the congest model. We show that we can schedule jobs in order of t divided by n plus local congestion plus dilation times log n rounds with high probability, assuming the knowledge of local congestion beforehand. Let us now talk about the applications of the scheduling problem. Do you recall the MIS problem? Ghaffar et al. Showed that there is an algorithm in the congested Clique model which computes MIS in order of log delta rounds with high probability. We analyze the message complexity of the algorithm and find out that it is order of n squared. Hence, using our random shuffling based algorithm, we schedule t instances of this job in order of t plus log delta log n rounds, which is basically the same as to say as we'll run large enough number of MIS jobs in constant amortized runtime. In this paper, we also apply our algorithm to obtain amortized algorithm for additional problem. We argue that the question of amortized complexity is interesting in congested Clique model. However, when developing fast amortized algorithms, we should also avoid solutions which result in large latency, meaning they take a long time before first job terminates. Let's sum up. We showed near-optimal scheduling algorithms in the classical congested clique model. These algorithms underline the importance of message complexity. We show that reassigning nodes allows us to better utilize the bandwidth of the congested clique model. Thank you for your attention. See you next time.